In this video, you're going to learn about elasticity. Elasticity is the property by which an object changes its shape and size under the action of opposing forces and recovers its original configuration when the forces are removed. Your elastic limit, when the body does not recover completely its original configuration because the distorting forces is too large, then the deformation exceeded the elastic limit. Inelastic or plastic materials, materials with very small elastic limits, examples of which are your dough, putty, and lead. Your Hooke's law states that the deformation of an elastic body is directly proportional to the applied force provided that the elastic limit is not exceeded. Your force F is directly proportional to the product of your spring constant K and X as displacement. Potential energy of a spring is equal to half of the product of your spring constant and the displacement squared. As the diagram expresses here, prior putting an object on the spring doesn't have any displacement. As the object with the force of its respective weight is exerted on the spring, a displacement is created as the spring is stretched. Now, the force exerted on the spring is equal to negative kx or negative spring constant multiply it with the displacement, okay? Or the amount of displacement. Why is it negative? It is negative because the force is in downward motion. Let's proceed with the stress. Stress is represented as sigma. It is the tensile stress with the ratio of the force to the cross-sectional area. Your sigma now would be equal to force F all over A or cross-sectional area. Strain is represented as epsilon. It is the tensile stress to which the ratio of the increase in length here is actually your elongation to the original length. So we have this formula for your strain. Your epsilon now, E is equal to elongation or delta L all over LO. Your elongation now or delta L is calculated as the stretched length of a body minus the original length of the body prior to subject to a stress. Now your epsilon is equal to your sigma or stress all over Young's modulus. Okay. Again, your elongation delta L is the change in length. Young's modulus is expressed as in terms of Y, it is the ratio of tensile stress to tensile strain. It is proportional to your strain. Now, if we're going to express in formula, your Young's modulus Y is equal to stress all over strain, okay? Delta F all over the cross-sectional area, all over your elongation, all over your original length. Elastic lag or hysteresis pertains to the failure of an object to regain its original size and shape as soon as the deforming force is removed. Okay? An example of these are your brittle metals. Okay? So we have this stress and strain curve. Your stress is in the y-axis, okay, sigma, and then your strain is graphed on the x-axis or your epsilon. Now, if a material is subjected to a strength or stress test, usually your steel rebars on a manufacturing site, if the material is tested, it will be graphically represented in elastic region and plastic region. The graph now shows the linear increase on the material's stress. Okay? This point pertains to the maximum allowable stress. It is also the proportional limit. Okay? The slope of this straight line here, prior to your proportional limits, it pertains to your Young's modulus. Your Young's modulus now is the ratio between your stress and strain, okay? Sigma L and epsilon L respectively. On this part, okay, of this graph, the maximum point here on your elastic region is actually your yield strength. And then once the stress of the material, okay, slowly decreases and then increases again, from the yield strength to the breaking point of the material or fracture is actually the plastic region. And then on this graph, okay, the maximum point of your plastic region is the ultimate strength of the material. Once it fails, we'll go to your fracture or break. The material breaks. So we have the following conversions of units. A Pascal is equal to a Newton per square meter. PSI stands for pound per square inch. The pound here is actually your pound force, not pound mass. So it must be lbf per inch squared. A PSI is equal to 6,895 Pascal, and a Pascal is equal to 1.45 times 10 raised to negative 4 PSI. An ADM or an atmosphere is equal to 1.013 times 10 raised to 5 Pascal, or it is equal to 14.7 PSI. Okay, so we have a tabular data about the modulus of materials. As you can see here on the leftmost part of the table, you can see variety of materials with their respective Young's modulus, bulk modulus, and shear modulus. Okay? So you see here, your liquids doesn't have Young's modulus, but they have bulk modulus. And they also don't have shear modulus. Okay? As for your solids here, your aluminum, bone, brass, brick, concrete, copper, ground glass, granite, hair, hardwood, iron, lead, marble, nickel, polystyrene, silk, spider thread have their Young's modulus in terms of 10 raised to 10 pascals. Okay? Then their respective bulk modulus and shear modulus values. And with that ends my presentation for the basic concept of elasticity.